is a gneissic rock, peninsular gneiss, charnophytes. These dark colored patches is light from see these dark colored veins, this vein. So these are the pseudoductiles. So these are the clasps. These are not broken, but along these fractures are developed and because of friction, the melting is happening. These are purely glassy. Why it is appearing dark? Because very fine grained materials are appearing dark, but the glassy will be further dark. And you may find some small clasps inside. While it is entering into the rock fractures, it is picking up this parent rock. The parent rock and small clasps you will find within this ductile vein. So you can vein very fine veins, very thick veins, anastomosing different ways. That to enter through these fractures, it requires very high pressure, high magmatic pressure, very forceful intrusion, very forceful. Otherwise, see the veins, very fine cracks they are being filled up with this material. So unless it has lot of pressure, it cannot enter into this minor cracks. So high magmatic pressure. When this is created, this fluid of the melt has high magmatic pressure. See these are. I will show you some more ductile veins. You are able to see now. Okay. You see how this has come. All these dark color materials are pseudoductiles. These are these area. You don't see it here. So you see the brachia. The rock is totally broken into small fragments by these fractures. So this is a brachia, fault brachia. So this we are talking about the devitrification. The pseudoductile part has been devitrified. So these are the microlites, feldspar crystals, very long, thin, needle shaped minerals. So this is a clasp. Within this pseudoductile vein. The glassy part has been decrystallized into these microlites. Yesterday I was telling the microlites. You see, this is for the small zooming, So this is a pseudoductile vein. These are the clasps. Original rock. Mostly quartz, some feldspars may be there. And these are the microlites. So from a common point, like star, they come up. Like this one. The small nuclei from where this type of radial growth will be there. So this is a nucleus. These are microlites. Mostly feldspar microlites. Depending on the melt composition, the minerals will be decided. See the pseudoductile veins. These are the pseudoductile veins. See how it is going. You have very thick vein, very thin veins, very minor hairline fractures along which these veins have entered. These are the microlites. So these are this is showed. See the microlites, just like small, dendrites like things. So these are the clasps. So this has been totally decrystallized or devitrified. These are the pseudoductile veins. You can see the minor clasp inside this. So pseudoductile vein like this one. are declassed. These are declassed. And if you see under a thin section, this type of things will appear. It is a pseudoclinic name. Okay. Now let us go to myelonites. This already we have seen, the sleep planes. So this type of deformation you will see in a myelonite. But in case of brittle deformation or a fault, this type of deformation will not be there. Now, what I will do, before going to myelonites, I will show you something. Come. Remove this one. The light. So, myelonites and ductiles here. This is yesterday we have started. Ductiles here. Understood? Let's see, I'll draw 3 diagrams to tell me what I am doing. Draw it. No problem? No. You are able to follow these diagrams, huh? You draw it. Let me see how many of you can draw it. So I have drawn 3 types of shear zones. Just like 3 types of force, you can have also 3 types of shear zones. Shear zones, I am just leaving this ductile part. I have told you why I am doing this. 3 types of ductile shear zones. So a normal slip, normal slip ductile shear zone. This will be thrust slip ductile shear zone. This is strike slip ductile shear zone. This is what? Now, so where will be myelonites? So myelonites will develop here. These are the place where the myelonites will develop. This is the place where myelonites will develop. So that is the ductile shear. So here myelonites will develop. Along this zone, but we will be able to see because this is the marker bed, we will be seeing the myelonites here. ठीक है ना? Now ठीक है ना? Now you imagine if I ask you this way, suppose I put a chalk here. I put a chalk here along the fault. Along the fault plane I will put a chalk. Along the fault plane I will put a chalk. ठीक है? Now, so that chalk, if it is put like this here, and if it is put like this here, I want to understand. So where it will rotate? The rotation will take if the chalk is put like this. If chalk is put like this, it will not rotate. If chalk is put this way, then it will rotate. Similarly, in this case, if I put the chalk, this will not rotate. If I put the chalk this way, this will rotate. You don't understand? Like this way. So this is a normal fault. Normal fault, it goes like this, you know. It goes like this. This is a normal fault. If I put the chalk here, then the chalk will rotate. If I put the chalk here, this will not rotate. Similarly here, it is a strike slip fault. Strike slip fault is like this. So if I put the chalk this way, then all it will rotate. Similarly this case, if I put the chalk here, then all it will rotate. Follow this point now. So now, a section perpendicular to rotation axis. A section perpendicular to rotation axis. Suppose this is the rotation axis. This is the rotation axis. So what I am telling? A section perpendicular to rotation axis. In this case, which is section perpendicular to rotation axis? This rotation axis is like this. So this face will be section perpendicular to rotation axis. Here you put the chalk inside. So this face will be the face which is perpendicular to rotation axis. Similarly, this face is the face perpendicular to rotation axis. So that section you know as vorticity normal plane. You understand that? Vorticity means rotation, just see rotation. Whichever is normal to that is vorticity normal plane. So in case of a normal fault, your vorticity normal plane, some people say VPP or VNP, let us write. That plane is vertical. In this case, plane is vertical. In this case, plane is horizontal. Understood this part or not? Tell me. Huh? नहीं समझा ना? Now suppose this is strike. Strike slip fault में कैसा होता है? Strike slip fault में ऐसा होगा. So which is the rotation axis? That is the rotation axis. So ये rotation axis को whichever is perpendicular means this is perpendicular. So this face is plane perpendicular to rotation. रोटेशनल एक्सिस को जो परपेंडिकुलर दैट प्लेन first is
normal and reverse board blackboard is the rotation.
is a
In the first case blackboard is the rotation means that
this one not the blackboard. You see how is this plane?
axis is like this.
Axis is this way passing through the
Like this is
front plane. हाँ
it is vertical like this.
ऐसा rotation is like this along the front plane. नहीं समझ
So
रहे
axis
हैं?
like this na.
हाँ
Then axis the rotation axis is
Yes.
blackboard is the
हाँ
plane.
blackboard को क्यों आप ले रहे हैं? Okay blackboard को ले रहे हैं। ये तो हम थोड़ा टिल्ट करके लगाया ना। Diagram is not the right angle to the सब टिल्ट करके लगाया हमने। Blackboard there is nothing called reference, you know. Normal fault is this is the normal fault. If you put a chalk here, then right angle to that is what is in normal plane. Understood na? But this plane cannot be what is in normal plane. Vorticity axis is this, rotation axis is this. समझा कि नहीं समझा? ये चीज आपको खास समझना है. Which is vorticity normal plane, which is vorticity axis. In a ductile cell.
So vorticity normal plane is perpendicular to the fault plane.
Perpendicular to the fault plane. Perpendicular, okay. Maybe. Huh?
I'm asking, I'm confused between vorticity normal plane and fault plane.
Fault plane. Okay. You see, suppose in this case the plane is vertical. Plane is vertical. So this is fault plane. Fault plane is vertical. So like the axis will be this way. Axis is this. Now this plane is the vorticity normal plane. Horizontal. Like that. Similarly here. Understood na? It is this way. So like this. Vorticity normal. Vorticity is the rotation axis around the front. तो किस तरह स्लिप हो रहा है? From the slip you can say now this is the rotation axis. So follow this point na. Now, so myelonites are developing here. Here also myelonites are developing. Here also myelonites are developing. है कि नहीं? Myelonites are developing along this fault zone. Now to study a myelonite, आप कैसे study करेंगे? Either in the hand specimen you will study, or in a microscope you will study. You have to cut a section because you have to prepare thin sections. You have to cut a section. Either we say it is perpendicular to vorticity or parallel to vorticity plane. तो वो section को study करना है. इसका मतलब है, suppose this is the vorticity and this is the vorticity normal plane. आपको ये section को study करना है. Not this section. Again I will tell. Confusing हो रहा है? Here, which section you should study? This section, horizontal section you should study. In case of thrust, you should study this profile section. In case of normal profile section, you should study. You should not study here. आपको तो myelonite इधर मिलेगा, but you will get myelonites here also. Along the fault plane you will get the myelonites. Either myelonites will be there, either myelonites will be there. Like here you will get myelonites. This section also you will get myelonites. But which section you should study? You should study this horizontal section. Then only myelonite features will be prominent. All sections will not provide similar features. समझा कि नहीं समझा? So you should study this one. Vorticity normal plane. That is where this oriented samples comes into picture. You have to collect a oriented sample in the field. Suppose you have been sent to the field. You are doing field work. You will get some myelonites here. You will get. So you will take a sample. So in the field you should decide which is the vorticity normal plane. तो फील्ड में आपको देखना है एंड अकॉर्डिंगली put a sellotape or some other marker, you say this is the vorticity normal plane. After coming back here, you take a section parallel to them. Then all your study will be complete. But for other thin sections like those who are doing metamorphic study or sedimentary study, they don't require this section to be studied. They require any section. You just take a sample from somewhere, आगे कहीं तोड़ के thin section बना लो. Every side will be similar. But for studying a myeloid, you require a particular section. So this particular section is very sure in the field. This is the vorticity normal plane. So I should see it in the field, then only I will collect the sample. So after bringing it here, you got a section, parallel to the vorticity normal plane. You are understanding this pattern? Unless you decide it in the field which is vorticity normal plane, यहाँ आके आप you will be confused. So कभी shear zone में आप काम करेंगे because the shear zone is much more academic interest. But इसका practical utility हुआ है particularly in the mineralized zones. Mineralized zones, like any mineralized belt, you see if you study in future, they are all concentrated along the shear zones. You see any mineralized belt, base metal, say copper, lead, zinc, tin, tungsten, they are all concentrated along the shear zones. आप कैसे स्टडी करेंगे? There you have to take the samples, bring it to laboratory, do some fluid inclusion study, whatever may be, So you should study those perpendicular sections or vorticity normal sections. You understand now what is the meaning of vorticity normal section? That is why oriented, there comes this oriented sample. In the field you should orient. Orient means you should identify which is the plane. Suppose you got a sample like this, you should see this is the vorticity normal plane and put a sellotape. This is the vorticity normal plane. So after going back to the headquarter, I should cut a section parallel to this. Because this is your section to be studied. So this identification you have to do in the field. You don't understand this point now. So this section this is called vorticity normal plane. Should study it. ठीक है ना? Now what I will do, I will take the example of this strike slips here. Others we will not use now as an example, but we will study a strike slips here and myelinoids from here. This section we are going to study. How a myeloid appears in case of strike slip. But follow this point. Now, if you see this, I will draw another sketch. Like this. ठीक है ना? काम में छूट गया. So this is the place you are to study. This section you have to study. You understand? This is the vorticity normal plane. That is why you are going to study. So if you enlarge it, how it will appear, like this now. Just enlarge. This will be this part. This will be this part. And here the myelinoids are developed. Here the myelinoids are. You just enlarge it. It cannot be single plane now. It will be a zone. So here the myelinoids are developed. So now, this will be the one wall. This will be another wall. These are the two walls. So this is one block. This is another block. Now this block has moved this side. This block has moved this side. ठीक है ना? This block has moved this side and this block has moved this side. So I will draw it with bigger sketch here. So this zone is your myeloid zone. Now, so this is one, this is other one. This part will be myelinized. This will not be myelinized. It will be parent rock will be existing. Protolith will be existing. Now this part will be only undergone the crystallization, magnetization. So here I have told you, we are now this deformation you are seeing was this ductile feldspar is brittle. So this is our situation. We are discussing to study the magnetics. Yesterday I told you that that is the case. I will show you what type of feature will be produced. Okay, na? I will show you one section, one photograph. Then you may have to see this section. This is a typical look of myelonite. Typical look of myelonite means there will be some very coarse grained materials, and between them will be very fine grained material you see here. So otherwise in a rock, you know, everything is uniformly crystalline. The size of the crystals are uniform. But in the myelonite you see this difference. There will be some very coarse grained materials which you say the clast. Surrounding that there are very fine grained matrix. So this type of difference, you know, makes it distinct from a normal rock. So this is a myelonite. Myelonites are basically, you know, in the field, they are very foliated rock. You see, foliations are there. You will find two types of materials inside these. One is very coarse grained materials, which you say as clast. So these are the clasts, and very fine grained, you see, layers. So these layers, you see these layers, those who are acquainted with petrography thin section. So those are the things, you know. So these are your feldspar clast. Feldspar clast. And these dark colored things, you know, these fine grained things, these are your quartz ribbons. Quartz ribbons. So these are the brittle part. This, you see the feldspar grain, it is broken into pieces. You see. This is small, large, and there is a layering in this. You see the layerings here. See the layerings here. So these are mostly made up of quartz. Though they are appearing dark, but they are made up of quartz. Understood, na? So those are the areas, you know. Area. These are the quartz ribbons. They appear dark. In the field, they appear dark. So this you can just replicate, you know. You can think of, we were discussing these things earlier, na? Just a minute. So those layers now which you saw now, they are these layers. This is a thin section of photo. We have studied earlier, slip planes, glide planes. These are the quartz ribbons. Here there is no clast. So here these are the quartz ribbons. So we go back. So this is the area. Fine grain layerings, you know. These are the quartz ribbons. You make a section here, you will find those things. And the other things are clast. So you will have a clast surrounded by this matrix of the quartz ribbons. Understood, na? So these ribbons, you know, these layerings, they define a foliation in the rock. They define a foliation in the rock. So that is called your myelonitic foliation. Myelonitic foliation. Myelonitic foliation. So myelonitic foliations are these layers, and these are the clasts. Follow this point now. Now,
Sir, in myelonite, my quartz is foliated not.
what is?
In myelonite, quartz is foliated.
Quartz is elongated.
Feldspar not.
Yesterday I told you the feldspar is brittle, strong. You know, it will not be foliated. It will not be like this. It is not soft. It will break into pieces. Whereas quartz is soft. That's why it will be stretched, you know. Understood now? I showed you a photograph before photograph. Was very much elongated, stretched. There is a difference between their ductility between quartz and feldspar. Feldspar is hard, whereas quartz is very soft. That is why they are forming these ribbons. Whereas feldspar is remaining like that. But if we increase the temperature, all these feldspar will become ribbon. So it depends on the temperature and amount of strain also. So these are those foliations which you say is myelolytic foliation. Now depending on the percentage of this mineral, how many clasts are there and how much foliation is there. So you can classify the rocks into protomyelonite, myelonite and ultramyelonite. You can have 90% clasts like a rock like this, you know. It is nearly 70-80% clasts are there. So it is a protomyelonite or between myelonite and protomyelonite. So this is somewhere there. But if their number is less, you know, the class number is less, you can call it a myelonite or ultramyelonite. Ultramyelonite has no clast almost. Everything is recrystallized, ribbons. You understand, na? So now you have two components, one is the clast and another is a ribbon. The matrix part is a ribbon. So it is my typical myelonite fluid. Then you go to the second photograph. Let us see the myelolytic foliations. See the myelolytic foliations. Here almost there is no clast. Clast है ही नहीं. See, all are stretched, you know. Very little classes, very small class here and there. So this will be ultramyelonite or myelonite or ultramyelonite in between. Because classes are absent. No? But earlier one is the protomyelonite. Lot of classes. Now let us see the other one. You see here, this is also myelonite. This part you see, this part. The clasts are all stretched, you know, very much highly stretched. So different types of myelonites. You know. Okay. Now come back to this figure again. ठीक है ना? Now this myelolytic foliation, myelonite foliation is designated as C plane. C plane. Understood? C, just C plane. So these are the C planes. These are the C plane. So there is a word called, what is that word called? This element means slip planes. C planes or C fabric. These are called C fabric or C plane. So myelolytic foliation is called C plane. So here which is myelolytic foliation? These are the myelolytic foliations. Planar features. So these are the C plane. That is why C is marked there. That is C. Understood this part? So these are the C. The foliation plane is C plane. And this is parallel to this one. So this is the boundary of the shear zone. This side is your wall. The other wall is here. So this is the slip plane. So these foliation planes, myelolytic foliation planes, they develop parallel to this main slip plane. Like this, you know. So inside that also you will find this myelolytic foliation, which is parallel to this. So in an area, you know, where you are working, you may not be able to see the boundary. But if you know these myelolytic foliations, you can approximately say somewhere, you know, parallel to this plane, the boundary will be existing. Boundary may not be exposed, but what is the orientation of the boundary? So suppose you are working like this, you know. Here you will find rocks are highly foliated, porphyroclasts are present. Understood? Now, if you cross over this, those type of foliation planes will not be there. It is homogeneous rock. So how to define the boundary? What is the strike width of the boundary plane? You cannot do it because it is not exposed. So you can take this orientation of these planes, you know, same as the boundary. It means that. So magnetic foliation orientation is same as this major slip plane. So follow this point now. So magnetic foliation indicates the boundary or the orientation of the major slip. Now, you see, so you will be getting something like this, you know. So class will be here and there. So these are the ribbons, magnetic foliations, like this. So these are your C. Follow this part now. What is C? Now I will show you another section, another photo. Now what is saying, you know, if you take it, so these are the clasps, clasps, or it is known as porphyroclast, porphyroclast. So what is the difference between porphyroclast and porphyroclast? Porphyroclast and porphyroblast, there are two terms, na? What is a porphyroclast and what is a porphyroblast? Porphyroclast has to do with the shear zone. Remember, porphyroclasts are to do with the shear zone, but porphyroblast in a metamorphic terrain. In a metamorphic terrain, when some minerals grow to very high, large size, that is a porphyroblast. No shearing involved, no shear zone is there. But if a shear zone comes into picture, bigger materials, you know, are known as porphyroclast. So clast has something to do with breaking, shearing, breaking or shearing, But blast is something related to growth. Suppose a garnet ferrous mica cyst is there, you know, like this, you know, micas will be there, and some garnets will be there which are very coarse in size. So these are fine grained mica, but there are some minerals like garnet, you know, garnet, storolite, they form very large in size. So they are porphyroblast. These are blast, porphyroblast. So it has nothing to do with shearing, but due to shearing, the original rock is broken into pieces. So that is the clast. Understood? Clast is represents the protolith, original rock, but blast is a larger growth of a mineral. Like, you know, I'll show you once. Because sometimes this type of question comes. Even people at higher stage, you know, they confuse. I'll show you one section. Go ahead. I'll show you. Porphyroblast and porphyroclast. You don't understand, na? So now coming to this malomate. So these ribbons, you know, if you see these ribbons, suppose this ribbon, you take a thin section. The ribbon आप देखेंगे ना, the ribbons will be like this, very long ribbons. And inside this quartz ribbons, this is a quartz ribbon. Quartz ribbon. If you see under microscope, so you know what is cross polar. Cross polar. Another is plane polar. You understand, na? Plane polar means where the nickels will not be crushed. Here nickels will be crushed. So if you cross this nickels, you know, cross polar condition. In plane polar condition, this will be appearing a single uniform grain, you know, like uniform. Nothing will be visible inside. But if you cross polar it, then inside this ribbon, you know, you will get small microscopic, you know, small quartz grains. They have developed inside this. So these are called very micro quartz grains. Micro quartz grains inside the quartz ribbon. So one externally which appears to be a single ribbon consists of thousands of very minor grains of quartz which are not parallel to this. The grains, the grains are elliptical. The grains are elliptical in nature, and the ellipse axis is at an angle to the ribbon. At an angle to the ribbon. This I will show you. So that means even though this is the magnetic foliation, but if you go inside of this grain, there will be thousands of small grains inside, just like pomegranate, small seeds are there. You will find so many minor grains which are obliquely arranged. They are not straightly arranged. This is called oblique arrangement. Oblique arrangement inside that ribbon. So this oblique arrangement of the grains, inside the ribbon. Let us see here. Otherwise, no problem. Little time is coming over it. अब देखो, this is the cross polar. This is cross polar. If you uncross it, this part, this layer, this layer will become white. If you uncross it, because everything is quartz here. Everything is quartz. There is no other mineral. But if you uncross it, the whole thing will turn into white. That is the ribbon. But if you cross it, cross polar, the individual grains will come out. Like this is a grain, this is a grain, this is a grain. So they will come out. So these grains, you see how they are arranged. If it is not clear here, I will show you somewhere else. Just I will show it again. I will come back to this. Don't do it. I want to show you a better photograph. Once you are convinced, can you see the ribbons? Ribbons are very prominent. So this is a ribbon. These are the ribbons. These are the ribbons. This is a ribbon. This is a ribbon. So these are the magnetic foliation. These are the ribbons. So what is telling inside the ribbon how the grains are oriented? That is what the discussion. अब देखो खाली I am not telling anything now. I will show you some more photographs. What he is telling you? If you see these grains, so he is talking about these grains. I will slightly modify, make it slightly bigger. So these grains, like this, so they will appear like obliquely arranged here, like this. So you can see the alignment this way, like this, like this, like this. So this is the alignment he is talking about. So this alignment of these micrograins, they define one fabric, which is called S fabric. S fabric. Now what is C fabric is your ribbon. S fabrics are these minor grains inside the ribbon. They are obliquely arranged. They define the S fabric. So together, you see a SC fabric in the rod. These are the SC fabrics, like this way. All the ribbons will be arranged this way. So this way is your S fabric. S fabric. So then you say the myelonite is having an SC fabric. Understood this part? So suppose the short load comes, what is SC fabric? So define what is SC fabric. C is the magnetic foliation. Then S fabric is the minor grains. Like this you define. Draw a sketch I'll show you some other slide, yeah, so that things will be further clear. Then you see two fabrics. So this is one quartz ribbon unit. This is one quartz ribbon. It is cross condition. Then you see some oblique grains inside. Not so clear. Not so clear. Let us go to something else. This one. Let us see this one. This one I will show you. It is to some extent clear, you know, like this. To some extent it is clear. Okay. Now let us go to next slide where let's see this one. So these are the quartz ribbons. These are the quartz ribbons. ये quartz ribbons. Let's see where it is. Can you see anything oblique here? Huh? No. Can you see the myelinatic foliations? Myelinatic foliations are these ribbons. This is thick ribbon. These are the ribbons. These are the ribbons. These are the myelinatic foliations. See carefully. Now see this part. You see. Here you just see. If you can. You see these grains, and these grains. You see how they are oriented. Can you see that? See, these are the dark color layers are the C fabric. ये myelinatic foliation है. But these are the oblique fabrics. These are the oblique things. Can you see the small grains here also? So those are the S fabric in the row. You see some more. If time permits next time. अब देखो ये सूट आएगा क्या आपने ऐसे oblique they are arranged, you know. You see. So these are the S fabric in that. So major foliation, this is the myelinatic foliation C, but the oblique one is S. So I will show you some other photographs next time, and then interpret this S signal. Okay. But fortunately next week I am not here.